At Rice, I teach a course for juniors in mechanical engineering called Modeling Dynamic Systems. In this course, the students bring their knowledge from physics and calculus together and see how we can develop mathematical models of these first and second order dynamic systems. We do time domain analysis and we give them a brief introduction to the theory of feedback control systems. Because a lot of the students haven't had hands-on laboratory experiments prior to coming to this course, a focal point is the hands-on lab experiences with the haptic paddle.
The haptic paddle is a simple 1 degree of freedom mechatronic device the students use to get a feel for a lot of things they learn in the lecture course. So with the haptic paddle, they learn about sensor linearization with the Hall effect sensor, time domain system identification of the motor and paddle parameters, as well as getting a chance to kind of get a feel for their first chance with a PD control. And at the end of the course, it culminates with rendering simple haptic environments with the paddle. The experiments provide a mechanism for students to reflectively combine theoretical knowledge from the lectures with experiences in the lab. Each lab moves through the subsystems of the haptic paddle, building on top of the previous one. First, students calibrate the Hall effect sensor and determine the rotational inertia of the paddle. Then, students get an introduction to the basics of DC motors. Next, students characterize first and second order systems on both the paddle and equivalent analog circuits. Then, students perform some time domain system identification on the complete paddle system before rendering simple virtual environments and teleoperation on the haptic paddle. The effect that these reflective discussions about the haptic paddle have on the learning in the course is the center of an ongoing multi-year study where we're looking at trying to tease out the connections made between, translating knowledge between the lab and the lecture and vice versa. If the goal was just to determine, the damping in our system, what could we do with the response that we just measured?
Well, we know what voltage we're putting in because we can measure that with the DAC.
Yeah.
So from there, and we know the inertia of it. So from there, it's pretty straightforward to just calculate, I guess, the overall damping from which we can get the friction in the motor.
So we calculated all of the resistance values for critical damping, but it looks pretty overdamped. Do you know why? What did we do wrong?
So the capacitance values that you're going to use in this, the capacitor has bound the values will be in. And so what happens may not be exactly what you calculated. So you may have to, experimentally determine what is critically damped. You know the ballpark of which then, but not the exact values.
Okay, so we should tweak on the potentiometer.
Yeah. What happens when you tweak it?
Okay, that's starting to look better.
So I like the wall, but it's kind of bouncy. How could we fix that?
So if you want to reduce the oscillations, you've got kind of two knobs you can turn. You have the proportional gain and the derivative gain. It's kind of like your spring and your damper. So you can think of them as virtual springs and dampers. So if you wanted to reduce the oscillations, which one do you think you'd change?
I mean, I guess we could make the spring less stiff.
But
that's going to make the wall pretty soft. That doesn't seem right.
Right, it's a virtual wall, not a virtual curtain.
Yeah.
What if we make the damping higher?
Definitely, you can increase your damping, but there's an upper limit though. So the one thing, it may not be perfectly clear, is that we're taking a analog position signal and we're differentiating it. And that's where we're getting our velocity for our derivative error. But there is some noise there. So you can't take it as far as you want. You're going to get kind of a degraded feel. You get some vibrations. So
Makes sense.
Tune it. The haptic paddle at Rice has undergone several design iterations over the past decade, all aimed at improving the performance while maintaining the low cost of the device. Recently, we've looked at adding different plants, different modules on the haptic paddle to try and broaden the range of sensors that the students get to play with and also create more challenging control problems for advanced courses such as design and mechatronic systems.
With the combination of these design modifications and our ongoing curricular development, we strive to further enhance the efficacy of the haptic paddle for hands-on learning of system dynamics concepts.